In this lecture, we will discuss some numerical problems based on first law of thermodynamics and see how the concepts developed on change in internal energies connection with the heat and work can be applied. Let us take a look at this question number 1. A 1 mole sample of monatomic perfect gas for which the constant volume heat capacity is equal to 3/2 R, initially at P1 equal to 1 atmosphere and T1 equal to 300 Kelvin is heated reversibly to 400 Kelvin at constant volume. Calculate the final pressure, change in internal energy, Q and work. So, first of all, let us see what is the information given to us. The gas is monatomic and perfect. The value of CV is given. Even if it were not given, we know that the value of CV for a monatomic perfect gas is equal to 3/2 R. Now, as we discussed in the previous lecture, that CV is equal to dou U by dou T at constant volume. It is always true for perfect gas. We can use this equation to get delta U is equal to N times CVM into delta T, where N is the number of moles and CVM is the molar constant volume heat capacity. So, from this we can easily get the value of delta U. Let us take a look at the slide. N, which is 1 mole, given information is given, CV is 3/2 R, and I will use the value of R in joules per Kelvin per mole, because finally I would like to have the answer in joules, and the temperature difference is 400 minus 300. So, therefore, the value of delta U after I convert into kilojoules come out to be 1.25 kilojoule. Very easy. Second, also note that the heating is done at constant volume. So, for any constant volume process connected with the PV changes of a gas, if the volume is held constant, there is no work done. So, straight away we can set W is equal to 0. So, if W is equal to 0, then I use the first law, delta U is equal to Q plus W, and immediately we get to know that delta U is equal to Q. And let us see the calculations. Since delta U we have just calculated to be 1.25 kilojoules, so Q is also equal to 1.25 kilojoule. Please note here that the heat is used to increase the internal energy of the system here, since no work is done. Whatever heat is supplied, that is directly getting converted into change in internal energy, that is adding up to the internal energy of the system. Now, the only thing which is remaining is to calculate the final pressure. The gas is ideal. So, whenever a gas is ideal, I can use the expression PV is equal to nRT, and initial volume can be calculated from N R T I upon P I. All the information is given, N is given, R we can choose of some suitable units, and initial temperature and initial pressure are given. Let us take a look at the calculations. N is 1 mole, and here I will use R in the units of liter, atmosphere, Kelvin inverse, mole inverse, because the pressure given to me is in atmosphere. So, after substitution we get a volume, initial volume of 24.6 liter. The given information is that the system is heated reversibly at constant volume, and here you see since the system is heated reversibly, that means it must be the pressure or the temperature, not the pressure, because if you change the pressure the volume will change. Here the temperature is being changed in a reversible manner in an infinitesimally small amounts. So, in order to get now the final pressure, P f will be equal to N R T f, and since it is a constant volume process I can use V I, which I just calculated. Look at the slide, V I comes out to be 24.6 liter, and the final pressure from this expression nRT F by V I will come out to be 1.33 atmosphere. So, the temperature is being increased, the volume is being held fixed. So, obviously, the pressure is going to increase. So, the pressure has increased from 1 atmosphere to 1.33 atmosphere. Now, let us take a look at a different type of question and see how to address that. Now, it is a question when the pressure is held constant. When 3 mole of oxygen is heated at a constant pressure of 3.25 atmosphere, its temperature increases from 260 Kelvin to 285 Kelvin. Given that the molar heat capacity of oxygen at constant pressure is 29.4 joules per Kelvin per mole, calculate Q, W, delta H and delta U. And also let us assume that the oxygen gas is behaving ideally. So, what is the information given? We are given that the process is a constant pressure process, and we also are given the increase in temperature. Okay. So, we can easily get delta H for this process from this expression. Cp is equal to dou H by dou T at constant pressure. So, delta H is equal to N times Cpm into delta T. If I take dt to other side, integrate and treat heat capacity at constant pressure as a constant quantity, means independent of temperature, then I can write this equation. The value of N is given, the value of Cpm heat capacity at constant pressure for oxygen. Oxygen is a diatomic gas. For a perfect monoatomic gas, the value of Cv is 3 by 2 R and Cp is 3 by 2 R plus R, which is 5 by 2 R, and here oxygen is diatomic. Therefore, the value of Cp for oxygen will be equal to 3 by 2 R contribution to CV comes from translational degree of freedom, and being a linear molecule another R contribution comes from the rotational degree of freedom. So, CV for oxygen gas will be 3 by 2 R plus R. This is due to translational degree of freedom, this is due to rotational degree of freedom, which is 5 by 2 R. And if you add another R to this, because Cp minus Cv is equal to R, or if I take the difference in molar heat capacities, Cpm minus Cvm is equal to R. So, Cp is going to be 7 by 2 R, 5 by 2 R plus R is equal to 7 by 2 R. So, I use this information to calculate delta H. Let us take a look at the slide. Delta H is equal to N times Cpm times delta T, N is 3 mole, Cpm as I just discussed is 7 by 2 into R. Let us choose the units to be 8.3145 joules per Kelvin per mole, and the difference in temperature is 285 minus 260 Kelvin. A point to be noted here is when you are using the difference, whether you use the temperatures in Kelvin or you use the temperature in degree Celsius, it does not matter. And the calculation suggests that the number turns out to be plus 2.2 kilojoules. And immediately we can from here only say that Q is equal to it is a constant pressure process is equal to delta H. So, this turns out to be also plus 2.2 kilojoules. Now, how do you calculate the value of delta U? There are two ways of calculating the value of delta U over here. One is that we know H is equal to U plus PV, and if I use it for a gas, perfect gas, U plus nRT. So, delta H will be equal to delta U plus delta nRT, and here the temperature is changing. So, delta H will be equal to delta U plus N R delta T. This equation can be used to get the value of delta U. Now, let us go back to the slide. So, delta U is equal to delta H minus N R delta T. We substitute the value of delta H as 2.2 kilojoule, N is equal to 3 mole, R is equal to 8.3145, and I divide by 1000 to convert into kilojoule per Kelvin per mole, and delta T is 25 Kelvin. You see delta U is turning out to be plus 1.6 kilojoule. I can also get the same number from the definition of CV, because CV is equal to dou U by dou T at constant volume. Although here the volume is constant, but as I discussed in the previous lecture that this equation holds true for perfect gases, whether the pressure is held constant or volume is held constant does not matter. So, therefore, delta U from this equation will be equal to N times CVM into delta T. And if I substitute the values, N as 3 mole, Cv is 5 by 2 R for the reasons that I just discussed, and temperature difference is 25 Kelvin, and you see you get the same number 1.6 kilojoule, whether you use the equation delta U is equal to delta H minus N R delta T or delta U is equal to N times CVM delta T, you get the same answer. Now, Q is equal to plus 2.2 kilojoule, that we have already discussed, because it is a constant pressure process. So, all the heat which is supplied at constant pressure is equal to delta H, and the value of work can be obtained by using the first law, that is delta U is equal to Q plus W, and as seen on the slide that W is equal to delta U minus Q, which is equal to 1.6 minus 2.2 is equal to minus 0.6 kilojoule. These are the numbers, but let us look at the meaning coming out from these numbers. The heat supplied is 2.2 kilojoules, and the change in internal energy is 1.6 kilojoule. That means, all the heat which is supplied has not led to increase in the internal energy, some of it has been used to do the work. That means the system has done some work, and that work of driving back the surroundings is equal to minus 0.6 kilojoules. Now, this is the negative sign which tells that the system has done the work. So, as I always have mentioned earlier, that in thermodynamics it is not just the numbers, but the sign also carries a lot of meaning. Now, let us take another type of question. Calculate the heat needed to heat the air in a house from 20 degrees Celsius to 25 degrees Celsius. Assume that the house contains 600 meter cube of air, assumed perfect diatomic gas. The density of air is 1.21 kilojoule per meter cube at 20 degrees Celsius. Also calculate delta U and delta H for heating of the air. It is an interesting question and will lead us to the calculation of the amount of heat needed to just increase the temperature from 20 to 25 degrees, that is just 5 degree centigrade change in temperature of the house. And the volume of air in the house, if we consider that the whole house is filled with air, of course it is, that means it is about one bedroom, hall, kitchen kind of apartment, 600 meter cube of the volume. So, here I need to calculate heat. So, heat we need to decide under constant pressure condition or under constant volume condition. A house has a constant volume, the volume of the house does not change, pressure can change. That means, we should target QV, which is equal to delta U. This is what we need to calculate. And delta U means we should now focus on heat capacity at constant volume. So, this will be equal to N times CVM into delta T. That means, now I need to calculate the number of moles, and in order to calculate number of moles, I need the weight of air, the mass of air present in the house. Since we know the density, I can easily calculate the mass. Mass is equal to volume into density. And once I know mass and if I know the molecular weight of air, I can easily calculate the mass of air or number of moles of air present in the house. Now, what does the air contain? Air contains nitrogen and oxygen in majority. Let us say about 75 mass percent nitrogen and about 23 mass percent oxygen, and remaining there are other gases. The approximate molecular weight of air is 29 gram per mole, and mass of the air can be calculated from volume and density. Mass is equal to volume times density, which is 600 meter cube into 1.21 kilogram per meter cube, which is 726 kilogram. And then the number of moles of air will be equal to the weight divided by molecular weight. The mass of the air is 726 kilogram, which is 726 into 10 raised to the power 3 gram divided by 29 gram per mole. So, the number of moles come out to be 25,034. So, once I have N, then I need the value of CVM, and since it is assumed a perfect diatomic gas, so therefore, CVM has to be used as 5 by 2 R. We just discussed in question number 2. So, I have the information on CVM, and we are already told that we need to calculate the value of Q for just a 5 degree centigrade change in the temperature, and just take a look at the calculations. Delta U, which is equal to N times CVM times delta T. You substitute the values of N, 25,034 mole, CVM as 5 by 2 R, and temperature change as 5 Kelvin. The value of delta U comes out to be plus 2.6 megajoule, and that is what our target was to find out. The heat supplied at constant volume, that means the amount of heat that must be supplied simply to change the temperature from 20 degree centigrade to 25 degree centigrade in a house of fairly 1 BHK. You require 2.6 megajoule of heat, and then by using appropriate equations, one can even try to find out the electricity bill that will come to just provide this much heating in the house. Next is to calculate delta H, and it can be calculated in the same way as we calculated earlier, that delta H can be calculated from N into CPM into delta T. Now, we have the value of N, CPM will be 7 by 2 R, and delta T is same, that is 5 Kelvin, and let us take a look at the slide. The value of delta H comes out to be 3.6 megajoule. So, you see the first law of thermodynamics allows us to find out many useful thermodynamic parameters which are either connected with internal energy or connected with heat, and also one can connect this with the work. Suppose if the pressure were kept constant, in the house we discussed that the volume is held constant. So, we need to calculate QV. If pressure were held constant, you see how much amount of heat would have required. You would have required more heat, 3.6 megajoule. Let us now solve the last question of this tutorial, which is the standard enthalpy of formation of gaseous water at 25 degrees Celsius is minus 241.8 kilojoules per mole. Estimate its value at 100 degrees Celsius. Given the following values of the molar heat capacities at constant pressure, water vapors is 33.58 joules per Kelvin per mole, hydrogen gas is 28.84 joules per Kelvin per mole, oxygen gas is 29.37 joules per Kelvin per mole, and assume that these heat capacities are independent of temperature. So, the information given is the enthalpy of formation or delta H of the reaction at 25 degrees centigrade, and we are asked to find out the value of delta H at 100 degrees centigrade. So, in order to connect these two parameters, we need the values of heat capacity, and the heat capacities, let us see how to get the value of delta Cp for the reaction. This is the reaction representing the formation of gaseous water, hydrogen gas plus half oxygen gas forming H2O gas. Delta Cp can be calculated from the molar heat capacities at constant pressure of product minus that of the reactants, and all the values are given. After you substitute these values, delta Cp comes out to be minus 9.94 joules per Kelvin per mole. The value turns out to be minus. So, therefore, try to assign some meaning to the minus sign. Using Kirchhoff's law, that is standard enthalpy of reaction at 373 Kelvin is equal to standard enthalpy of reaction at 298 Kelvin plus integration from 298 to 373 delta Cp dt, and since it is given that the heat capacities are independent of temperature, delta Cp can come out of integral, and then this calculation suggests that the answer comes out to be minus 242.6 kilojoules per mole. So, you see the value of delta H at 25 degrees centigrade was minus 241.8 kilojoules per mole, and the value of enthalpy change at 373 Kelvin is minus 242.6 kilojoules per mole, which is more exothermic than the one at 25 degrees centigrade. Although in this example the difference is not very large, but this difference is actually decided by the connector delta Cp, because the delta H at a final temperature is equal to delta H at an initial temperature plus, if I treat delta Cp to be independent of temperature, Tf minus Ti. So, it is this value which is a main decider for how the enthalpy of the reaction will be affected when the temperature is changed. So, I hope that these numerical problems have made the concepts more clearer. In case there are any queries and questions, please do write them down, and ask us during the help session. Thank you very much.